Next, we'll talk about statistical power. Oftentimes, it's just referred to as power. So statistical power is the probability of rejecting the null hypothesis when it is false. So you want to reject the null hypothesis when it's false. So having a greater probability of rejecting a null hypothesis when it's false is good. So you want high statistical power when you're doing your research. So I drew the table here of decision errors. And just as a reminder, right here is reality. So either the null hypothesis can be true, in which case SEU men are just as tall as American men, or the null hypothesis can be false. So for example, SEU students can be taller than American men. And if the null hypothesis is true, recall, we can reject the null hypothesis when we shouldn't have, and that is a type 1 error. Alpha is the rate at which that happens. Remember, we usually set alpha at 0.05, so that when the null hypothesis is true, only 5% of the time do we reject the null hypothesis, and that happens because of sampling error. Hopefully, though, if the null hypothesis is true, we fail to reject the null hypothesis and say, oh, our research didn't show anything interesting, we can't publish it. All right. So now notice statistical power is relevant when the null hypothesis is false. The null hypothesis is false in reality. So statistical power is only relevant here. So this is what we're working with now when we're talking about statistical power. Now for statistical power, right, the null hypothesis is in fact false, and we either reject the false null hypothesis, which is what we want to do, and we publish our findings. Or we fail to reject. Right? These are the only two decisions we can make when in reality the null hypothesis is false. So beta is when we fail to reject the null hypothesis when we should have. Right? And statistical power is the probability of rejecting the null hypothesis when it's false. Rejecting the null hypothesis when it's false. So this here is where power is. Power is the probability of rejecting the null hypothesis when it's false. Beta is the probability of failing to reject the null hypothesis when it's false. So power's formula is 1 minus beta. Because altogether, when the null hypothesis is false, the probabilities have to add to 1. And if you're failing to reject the null hypothesis incorrectly, that's beta. So everything else, the only other decision you can make is to reject it like you should. And so any remaining probability would be up here. So power also goes up in this cell of the decision error matrix. So when researchers are planning their studies, what they're hoping to have is a statistical power equal to 80%, or equivalently 0.80. Right, so that would mean that the probability of rejecting a null hypothesis when it's false is 80% or 0.80. So to translate that into lay folk terminology, if you have a statistical power of 80%, then 8 out of 10 studies would reject the null hypothesis when it is false. Right, so consider another example. Let's say you have power of 50%. That means if you do your study and there really is an effect that's consistent with your research hypothesis, only 5 out of 10 or 1 out of 2 times, only half the time would you even get a significant effect. So a power of 50% is actually a very low power. Half the time that you do your study, you're going to be wasting your time because you're going to fail to reject a null hypothesis when you should have. Right? So 80% is kind of a social convention that researchers have agreed. Right? So in that case, 8 out of 10 times you'd reject the null hypothesis when it really is false. So let's work through an example of actually calculating statistical power. So we'll work with the familiar example of the research hypothesis that SUU students are taller than American men, right? Because we know the population mean and standard deviation for American men. Right, so here's the population distribution. Its mean is 70. The standard deviation is 4. If this is our sample down here, we'll say our sample size in this case is 9, just to keep the math a little bit easier. We'll say the standard deviation of our sample is 4.2. It doesn't actually come into play here. And we'll say our sample mean is 74. And then, of course, we can do our sampling distribution, right, which doesn't depend on this at all. Our sampling distribution is going to have the same mean as the population distribution, and its standard deviation is going to be the population standard deviation divided by the square of the sample size. So 4 divided by the square root of 9, 4 divided by 3, 1.33 is going to be the standard deviation of this distribution. Our critical values on this distribution, right? So these are the values where if our sample is more extreme, we'll reject the null hypothesis. So this is a normal distribution. We're going to set alpha at 0.05. So far we're just going through the regular steps of a z-test here, right? And so if you look in the z-table, you split this between the two tails so that there's 0.025 on each side. Right, then the z statistic over here is 1.96, right at the edge there, and this one is negative 1.96. Right, and so these are z statistics that are the z critical values, and up here this is height in inches. So far everything we've done is just the regular steps for a z-test, but now we're going to switch over, and now we're going to focus more on statistical power. So to calculate statistical power, you have to have an estimate or knowledge of the actual height of SUU men. So let's say that we do know SUU men's heights, and it is 74 inches, and we'll say the standard deviation of SUU men heights is the same as the population, 4 inches. I'm going to create a little space here. So if SUU men's heights are 74 on average, that means their distribution is shifted over, and it is centered on 74 here. Notice this is in this case we're talking about a Cohen's d equal to 74 minus 70 divided by the standard deviation. A Cohen's d equal to 1. So this would be considered a large effect size. And now what we're going to do is we're going to calculate the probability of rejecting the null hypothesis when it's false. Now in this case the null hypothesis is false because SUU men's population mean height is 74. 74, that's 74. 74 is not equal to the population mean for American men of 70. So we're working with a scenario now where the null hypothesis is false. Now we want to calculate the probability, given this study, of actually rejecting the null hypothesis. So what we've already done with the black color here is we've determined our decision cutoffs for where we're going to reject the null hypothesis. So any samples that we observe that are above 1.96 on this distribution or below negative 1.96, any samples more extreme, we're going to reject the null hypothesis. So now we got to figure out what percentage of samples from this true population are beyond those cutoffs. Right? So what we're going to do is use the true population for SUU men, and we're going to figure out what kind of samples we would expect from that population. Right? So the logic is exactly the same as it was for the null hypothesis. for creating the sampling distribution. We're just using a population distribution shifted over. Right, so this sampling distribution is going to be centered on 74. So this is going to, we'll call this the sampling distribution mean for SUU students. It's going to be the same as the population. And its standard error, it is going to be the same as it was for the population, because the same values are going to go into it. Right? We said 4 and 4. So its standard deviation is going to be 1.33. So remember before we decided our cutoff using this black distribution, which assumes the null hypothesis is true. But in this case, the null hypothesis isn't true, just like we were hoping when we started our study. And so what we're going to do is we're going to figure out what percent of these samples on this distribution are beyond the cutoff. And that percent is our power. All right, so I'm going to redraw this larger over here, do a zoom in so we can see what's going on a little bit more clearly. So what I've tried to do over here is redraw the sampling distributions, hopefully pretty closely to scale. So black is the expected sample distributions, assuming the null hypothesis is true. Red is the expected sample distributions given the true population of SUU students being taller than American men. So the red is where the real samples are going to be coming from. Black is where we have our decision cutoff set up. Remember, so our Z statistics here, our Z critical values, are to have .025 on either side, right? Because our alpha is .05. And now what we want to do is figure out what percent of the actual samples that we'll observe are going to be beyond that cutoff, in which case we'll reject the null hypothesis when we should. So the area that I covered in here is the power. That's the probability of rejecting the null hypothesis when it's false. And in this case it is false because the population mean is really 74, not 70. So now we're starting with knowledge about where the cutoff is on the black distribution, but we have to convert that into knowledge about where that cutoff is on the red distribution. Right, so the first thing we're going to do is we're going to change these, in fact, this Z statistic into a height value, and then we can calculate that height value's Z-score on the red distribution and figure out what percent is to the side of it. Okay, so we need to calculate 70, right, and we're going over, so we're adding, so the Z-score is positive 1.96 standard deviations. And so we've got to figure out how big is each standard deviation. Each standard deviation was 1.33 inches. So this will allow us to translate 1.96 standard deviations into inch units, and we're going to add that to the mean to figure out how many inches is right there. So you do the math and you should get, if I did my math correctly, 72.61. So now what we're going to do is we're going to calculate the Z statistic of 72.61 on the red distribution. Right, so we need to turn this raw height unit back into a Z statistic, a Z-score, on this red distribution so we can use the Z table. All right, so the Z statistic is the score, 72.61, minus the mean, 74, divided by the standard deviation, 1.33. Okay, so we're subtracting a larger mean, so it's going to be a negative value. And when I did my math earlier, I got negative 1.05. Right, so on the red distribution, the Z-score, where that critical region's edge is, that Z-score is 1.05. So 1.05 is where we're looking at there. So now we can go to the Z table and we can figure out what percent is above and below a Z-score of negative 1.05. So when I went to my table, it said the percent of this red distribution that was beyond the z-score of 1.05 was 14.69%. But we want the percent that's on the other side, so we can subtract this from 100, in which case this area, 100 minus 14.69 is 85.31. So 85.31% of all the samples that you would expect from this population are going to exceed our decision threshold, and we're going to reject the null hypothesis like we should. So in this case, in this example, the statistical power is 85.31%, so that's a really nice statistical power. Now if we want, and that ends the whole calculation of power. Notice we never figured out, given our observed sample, if we're going to reject the null hypothesis or not. That's a separate question than the power. The power can be calculated completely separate from the statistical test itself. So this is power, the probability of rejecting the null hypothesis when you should. And this blue one here, this is beta, the probability of making a type 2 error, the probability of failing to reject the null hypothesis when it's false, right? And so we actually calculated power by using the power formula of, in this case, 100, because we're working in percents, minus beta. So if we were working in proportions, it would have been 1 minus beta. In practice, calculating statistical power is really challenging because to calculate power, you have to know the real population parameters that you're interested in. And if you know those population parameters, if you know the height of SUU men, then you usually don't even need to do your research project, because that's what you're trying to figure out, is what the height of SUU men is like. So in practice, you can't calculate the actual statistical power. There's two other solutions though. One is you could guess the effect size, the population difference, based on looking at previously published research that looked at really similar topics. So if somebody else did a study where they looked at the average height of BYU students, we could use that as our guess for SUU men's heights and calculate a statistical power. It's an estimated power, but it'd be something to work with. So for that, the effect size is estimated. And the other approach is you could use a minimum effect size of interest. So if you're only interested in the case that Cohen's d is at least 0.5 or larger, well, then you can set Cohen's d to 0.5, calculate how far the population means would be different, and calculate everything you need to determine your statistical power, assuming that in the world the Cohen's d is 0.5. It doesn't mean you're right. So in fact, that's another way of estimating the statistical power. You might be right and you might be wrong. It could be an over or an underestimate. So there's 5 ways to increase your statistical power in your research. The first way is to increase your sample size. So here we had a sample size of 9, but if you increase your sample size, you increase your statistical power, because sample size is part of the formula for how wide the sampling distributions are. The larger your sample size, the smaller your standard error. So if you have a 2 on the bottom, you'll end up with a half, but if you increase the number on the bottom, you end up with a smaller resulting number. So the larger your sample size, the more these are squished in, and if you keep the means the same, there's just less and less overlap between the two, and that pulls the critical region this way, while also at the same time pulling the expected sample means away from it. So you end up with more statistical power if you increase your sample size. And in practice, this is the best way to increase your statistical power, is to have a larger sample size. The second way to increase your power is to increase the difference between your two population means. You couldn't do that with this example we're working with here, but let's say you're looking at the alertness of a caffeinated and a decaffeinated group. You might be able to increase the difference in alertness by making your caffeinated beverage have more caffeine in it compared to a less caffeinated beverage. So that could push the means apart, and therefore that push these means apart, pushing these means apart and give you more power. A third way to increase your power is to decrease your population standard deviation up here, which of course would decrease the sampling, the standard error down here. And the best way to do that usually is to have a more reliable measure of whatever you're measuring. A more accurate measure will end up having a little bit less error there, but in practice, people usually work with the best measures they can anyways. The fourth way to increase power is to increase your alpha. Alpha of 0.05 actually is already a pretty risky rate of accepting false positives, and so I strongly discourage you from increasing alpha. And the fifth way to increase your statistical power is to go from a two-tailed test to a one-tailed test. So that would switch all of your critical region to one side. So you'd end up with a little bit extra there. But the reason you shouldn't do this is discussed in the other video about one versus two-tailed tests. And two-tailed tests are almost always preferred to one-tailed tests. So one problem with using a two-tailed test is you have a little bit less statistical power, but the benefit is you don't artificially increase your alpha. And if anything, there's a problem with false positives in the literature right now. So these two approaches should not be used unless you have very good justification. So the main way you should really try to increase your power is by increasing your sample size in practice.